Just to finish up that last problem, I got cut off when the timing ran out. To calculate the final Simpson's rule approximation, take 1/8 over 3, which is 1/24, and plug in each of these endpoints into the Simpson's rule formula. You first take f of the first number, 4 times f of the second number, 2 times f of the third number, and you repeat the process 4, 2, 4, 2 all the way until you reach the last value. You'll place that into f of 2 with no coefficient, and your arc length approximation should be 1.132. For our next example, we will take a look at a function where there is no upper bound. Find the arc length of y equals e to the x over the interval 0 to a. Just to give you a visual idea of what this looks like, I'm going to pull up an applet. Here is our function, and I'm starting it at 0, and naturally as I make the upper bound larger and larger and larger and larger, the arc length increases very quickly. I'm only at x equals approximately 3, and already the arc length is upward of 18. Now the more segments you use, obviously it hugs a lot better, and that's what our formula tells us. It gets us really close to the actual length of the arc. We're going to try a problem now where there's no upper limit. And for problems like that, we execute them just like before, except now our upper bound is going to be a instead of a number. In this problem, we'll take a look at e to the x over the interval 0 to a. Just as in the previous examples, we'll first start by finding the derivative, which will be e to the x itself, square it, and add 1. When we get ready to throw that under the square root, we notice that this might not be the easiest thing in the world to find the integral of. So, we will need to use a u substitution. We're going to let u equal the entire inside portion of the radical, and the radical itself actually. So we're going to let u equal the square root of 1 plus e to the 2x. Then du, if you use the power rule, the radical has an exponent of 1/2. So that exponent gets dropped. This term right here with power half on it, we subtract 1 from it. So it goes to the bottom as a power negative half. And then we multiply by the derivative of the inside. The derivative of the inside, 1's derivative is 0. E to the 2x's derivative is 2e to the 2x. So that's where that came from. And it turns out our du equals 1 simplified e to the 2x over, the 2's will cancel out, e to the 2x over the square root of 1 plus e to the 2x. dx. And the reason we chose to do a u substitution is now we can take a look at what we have and rewrite our du actually in terms of u. We note that the bottom portion of our du, the square root of 1 plus e to the 2x, that was our original u itself. Alright, so we're just noticing that in the du we actually had u itself. That's where I'm getting this u from. And the top is just e to the 2x. Where could that have come from? If we square the u, we get 1 plus e to the 2x, just the inner part. And then if we take away 1, the 1's would cancel out, and we get just e to the 2x. So the substitution we're going to make actually ends up being really nice. Let's get rid of these traces here. Alright, so we're going to take our expression, the square root of 1 plus e to the 2x, and we're going to send off this into it. Note that here we have our original function. Here is our original u. That's in green. And in blue, our dx gets replaced with the second expression here, u over u squared minus 1. And that comes from taking du equals u squared minus 1 over u dx. and solving for dx. To get dx by itself, we invert the fraction, and we get dx equals u over u squared minus 1 du. You see that? Just these blue terms right here. We're inverting it, multiplying both of the blue terms by u over u squared minus 1. That leads us to our integral here. We have u squared over u squared minus 1. And as we talked about back in chapter 7, when the highest powers are the same, we need to use long division so that we don't have the same exponent on the top and on the bottom. So the result of this step right here is doing the polynomial long division. U squared goes into u squared minus 1. Scratch that, I had that backwards. U squared minus 1 goes into u squared one time, and the remainder is a single one. So we can put that over what we divided by. So I have 1 plus 1 over u squared minus 1 is an equivalent expression to what's here by long division. Finding the integral is a little easier now because you can take what you have and decompose this term into partial fractions. Okay? If you have a piece of notebook paper right now, take it out, try using partial fractions to decompose this function. You can factor it into u minus 1, u plus 1, and simply use an a and a b. A over u minus 1 plus b over u plus 1, and you could decompose it from there. You should get half and negative half as your coefficients, as shown here. Okay, so that's just taking the fraction, decomposing it into partial fractions, and the rest is easy. Now we can find the integral. Each term integrated with respect to u. I have a u, half ln u minus 1, and another half ln u plus 1 with the minus sign in between. And from here, all we want to do is evaluate our answer. Plug in your a, but first plug u in. We didn't plug our u's back in. We want to substitute that back out. So for each u that's in the problem here, you want to throw in the square root of 1 plus e to the 2x back in. So that's where this came from. And does anybody know where this came from? This came from the fact that we're subtracting two natural logs. So we can write it as just a single natural log and make it a quotient. So this u was replaced with this square root minus 1, and this u was replaced with its square root expression, then the plus 1. So this was just a condensed version of what was laid out here. We applied the difference property and made it into a quotient. So that's how we got that step. And now we can plug in a, since we're back in terms of x now. Plug in a into the function first, and then plug 0 in, being ultra careful. When you plug the 0 in, the things don't cancel out. You actually have numbers you need to account for, and that's all of these. They don't zero out. And at the end, if you'd like to, not mandatory, you can simplify your answer a little bit here by multiplying this out, but it's not required. You can stop actually right here and be fine with this start answer. So as you can see, the function seemed very innocent, but once we plugged it into the square root and tried working it out, it actually opened up a big can of worms. But this is how you would calculate arc length given no specific upper bound. One could use this formula and supply their own upper bound and determine what the arc length is from 0 to their own upper bound. Next, we move to a formula for the area of a surface of revolution. In this little part of the lesson, we're going to take regions and spin them around to create 3D shapes, and instead of calculating volume like we did earlier in the course, now we're going to calculate surface area. And the formula for it looks very, very similar to that of arc length. We have the same conditions before. We need a derivative available, positive function, and also continuous, the surface area can be found using this formula. The main similarities are the bounds a and b. The square root of 1 plus the derivative squared is still there. The new additions for surface area are 2 pi and multiplying the integrand by f of x. This first example comes straight out of the book, and I think this is one of the more believable examples. Some of you may know the formula for surface area of a sphere from high school geometry. If you do already, jot it down now, because at the end we'll compare it and see if we got the same answer. In order to calculate the surface area of a sphere of radius r, we take the equation of a circle that goes from negative r to r, and we just take the top half, the semicircle. So the way this starts is we want to think of a circle with equation x squared plus y squared equals r squared. And to get the top part of the circle, we solve it for y. We're going to get a plus or a minus because we're taking a square root. And when we do that, we want to take the positive half. So we have the square root of r squared minus x squared. That would be the equation for the top part. If we rotate this about the x-axis, we can get a sphere. And we can use this formula to calculate its surface area. So here's what we want to do. Just as before with arc length, we want to find the first derivative of the function. Since we have r squared minus x squared, we use the chain rule, keeping in mind that r is a constant, so we're going to leave that alone and just differentiate the x. We're going to differentiate with respect to x. So applying the chain rule, we drop the half, decrease the power by 1, so our square root now went to the denominator. Then we multiply by the derivative of the inside, which is negative 2x. That's where our negative came from. And the 2 from the top and the 2 from the half from before cancel out. So here's our derivative. Then we add 1 to it after we square it. So the derivative squared, that square root disappears when you square the derivative. So notice it's gone. The top goes up an exponent and it turns positive. Then we want to add 1 to it. Alright, and to add the 1 to it, we just turn the 1 into a fraction. We turn the 1 into r squared minus x squared over r squared minus x squared. This way there's a common denominator, and I can add that up with the second fraction. The negative x squared and positive x squared cancel out. So here's what we're going to toss under the square root. Applying the formula, I have 2 pi from negative r to r, f of x square root 1 plus f prime of x squared. Plug all the information in. Notice here we have our f of x, and notice here we have the square root of 1 plus f prime of x squared. So that meant we took an r off the top, and we took the square root of the expression on the bottom. And it becomes a very simple problem to solve because the r squared minus x squareds within the integrand, they'll cancel each other out. So all you're really integrating is r with respect to x. You can even take out the r, stick it with the 2 pi, and integrate 1 with respect to x from negative r to r. That evaluates out to 2r. Then you have the 2 pi r out in front of it. That multiplies out to 4 pi r squared, which is the surface area formula for a sphere. So if you wrote this down in the beginning, you have the right answer. Congratulations.